Here we're now in the architecture management part of the platform, the home of models. After associating use cases with requirements, the next step is to build a functional model for each use case. That can be done with activity diagrams, sequence diagrams, state machines, and so on. For example, here are the sequence diagrams that describe the manually directed flight use case. Let's open this one. What happens when the drone is forced to make an emergency landing due to low power? Now, if I want to run a simulation, then I need a little bit more capability than a web browser can provide. I need a desktop client. I need Rhapsody. But there's a very tight link between the web client and the desktop client. If I click here, then this sequence diagram will open in Rhapsody. Let's briefly explore this part of the model before we actually go ahead and simulate it. First off, as we saw in the web client, this sequence diagram has a refined traceability link to a requirement. But there are other model elements, there are other sequence diagrams, for example, and we can view and add new traceability in various different ways. For example, this table shows me the sequences and the requirements that they're connected to. And I can add new traceability links directly in that table. I can also navigate from Rhapsody to the requirement. If I select Navigate to Original Tool, then I'm taken into the requirements management part of the platform, and that requirement becomes selected. Let's return to Rhapsody and explore the model a little further. This sequence diagram describes a specification for how the system, that's the vertical line in the center, should interact with elements outside the system context. In this case, that's the bird feeder on the left. In the context of a scenario, in this case when the hummingbird has to make an emergency landing due to low power. Sequence diagrams can be used to guide the designer as to the behavior of the system, and they can also be used to later test that same behavior. They also form the basis for defining interfaces. This diagram shows more of an architectural view of the system and its connections to things outside, along with a detailed view of the operations or internal system functions that the system can perform. How and when it performs those functions is determined by its behavior, and in this case that's been modelled using a state machine. State machines describe the modes or states of the system, and how and when the system changes state in response to stimuli, and what it does when that happens. Usually that's triggered by the system receiving a message from something in the system context, and that communication is detailed in the sequence diagram we saw earlier. So we have several different views of the system under design. Let's now run a simulation and bring those views together. When I execute this model, we have another view. Panel diagrams allow engineers to create simple mock-ups of user interfaces or test benches for use in stimulating the execution of the model, and that's what we'll use to drive our simulation. We also have an animated view of the original sequence diagram. This one will draw itself as the system executes, showing us the actual messages being exchanged and the actual system functions as they occur. Lastly, we can open an animated version of the state machine, which will show us the current state the system is in and any state transitions that occur. Here we can already see that the system is in the flight disabled state, waiting for a request from the bird feeder to enable flight. Now I'm in control of this simulation. If I click pause, then I can inject events and I can set data values, and nothing will happen until I tell the simulation to continue. For example, I can switch back to the panel and I can send an enable flight command. Then if I click go idle, we can see what happens. First, the panel shows me the system has changed its status to in flight. The animated state machine shows me that the system has changed state. It's now in the flying state, which also has a bunch of orthogonal regions. The animated sequence diagram shows me the request coming into the system and the internal system functions that were performed in response. Okay, let's switch back to the panel And we'll send the UAV off in a specific direction by dragging the sliders and then clicking the Set Direction button. This time I'll click Go to allow the simulation to continue on its own until I tell it to stop. Note that the panel now shows the power starting to drain away and the altitude starting to rise. The animated sequence diagram shows us the communication as it happens. And if we switch to the animated state chart, we can see that is now showing us live state changes. Back on the panel, we can see the power draining away. And when it reaches a specific threshold, which in this case I've set to 1000 units, the system automatically engages an emergency landing. If we switch back to the state machine, we can see we've changed state into emergency landing, and we can drill down into that emergency landing state and see what's happening inside it. Now that we've modelled and executed the system at a functional level, we can develop a system architecture and we can partition that behaviour across those subsystems. We can then create a handoff package to allow the subsystem teams to continue the work. That package comprises a set of model artifacts and also the corresponding requirements that go with them. For example, here in the modelling world, we have a handoff package for the avionics subsystem. That includes a set of scenarios that describe how the avionics subsystem interacts with the other subsystems. These scenarios allow the interfaces between the subsystems to be automatically generated. And then interface diagrams, such as these, also form part of that handoff. We've seen planning, we've seen requirements management, and now we've seen architecture management. Next, we'll look at testing.